Welcome to lecture 16. So this lecture is on real-time task scheduling in multiprocessor and distributed systems. So what we really need is that you need to go back to the Thals effect that was covered in lecture 15 and look at a very simple case where it was actually not possible to schedule a multiprocessor system, right? In the sense that it was not really possible to do a scheduling with EDF and RMS. But of course, by basically taking a job, splitting it and moving it to different CPUs, it was possible to do that. But here we will look at something slightly different. We will look at how inefficient scheduling can possibly be in a multiprocessor system. So let's start with the assumption the setting is we have M processors. So given the fact that the utilization of any processor is less than equal to 1, the combined utilization of the M processors is less than equal to M. All right. So now let's consider our task set. So I'm sort of going bottom up. So assume that I have M plus 1 tasks, where again M is the number of processors, and the execution time of each task is 1 plus epsilon. All right. So what is the utilization I'm looking at? It is M plus 1 multiplied with 1 plus epsilon divided by the period, where in this case period and the deadline are the same, and this is basically a period of 2. So mind you, the property on epsilon is that epsilon could be a very small number which is greater than 0. So as epsilon tends to 0 but it still remains positive, this tends to m plus 1 by 2, and again for large m this more or less tends to m by 2, right? So we are looking at a system with a roughly 50% utilization, right, of the entire system, where utilization is computed the way we do for typical multiprocessor or multi-core systems. So, interestingly, it turns out that even at a 50% level, which is way lower than what RMS gives us with infinite tasks in a uniprocessor system, which is 69%, even here also, this simple system of m plus 1 tasks with execution time 1 plus epsilon is not schedulable. So, you can look at all possible combinations, but pretty much if, let's say, you're not migrating, then the execution time of both is 1 plus epsilon and 1 plus epsilon. So the total is 2 plus 2 epsilon. And 2 plus 2 epsilon is clearly greater than 2. So this task will miss its deadline. And now if you decide to split the tasks, you can split and move any way you want. That is still not going to actually make the task set schedulable. So which essentially says that so mind you, this is for a static priority multiprocessor scheduler, right? We are not looking at a dynamic priority scheduler over here. So basically whatever I said has to be seen in the light of the fact that we are looking at a static priority scheduler. So here this cannot exceed half of the maximum theoretical utilization, because as you can see the maximum theoretical utilization is m, and this is m plus 1 divided by 2. All right. And that's the broad idea, that RMS on a single uniprocessor, the lowest it can go down to is 69.2%. But here even something which is very close to 50% is not schedulable. So here one thing needs to be understood, that if instead of static priority, if we have dynamic priority, or let's say if we are allowed a more intelligent way of moving tasks around, then this becomes schedulable. So let's consider an example. So assume I have 3 tasks, right? Their execution times are 1.1 and the period and the deadline are both 2. So then what I can do is that if I have the two processors P1 and P2, right? So this is, let's say, processor P2, this is processor P1, and the tasks are numbered T1, T2, and T3. So what I could do is that I could divide time into four intervals. The first zero point 0.5, second zero point 0.5, all right, and third zero point 0.5. So then I could schedule T1 over here, T2 over here, and then again I will schedule T3 over here and T1 over here. So basically, after 1 unit of time, what will happen? T1 will have executed for one time unit, T2 and T3 for zero point 0.5 each. So again, what I will do is I'll execute T2 over here and T3 over here. So after 1.5 time units, all three of T1, T2, and T3 would have executed for 1 unit each. So then how do I accommodate the next point 1? Well, that is quite simple. I can just, I'll have zero point 0.5 time units remaining. So what I can do is for zero point 0.1 time units, I can run T1. Then for zero point 0.1 time units, I can run T2. And then for zero point 0.1 time units, I can run T3. So if you see that if I am able to dynamically change the notion of priority and make it more intelligent, these set of tasks are indeed schedulable. But if I assume static priorities, in the sense if one task always has more priority than the other, right, which is not the case incidentally in this, then they are not schedulable. So we need to compare it with RMS. So what RMS was doing for uniprocessors, this needs to be compared with that. So now the question is that given the fact that it is hard to come with algorithms that have such beautiful bounds as EDF and RMS in a multiprocessor system, our key task is that how do we actually create good heuristics to schedule tasks. So here are some heuristics. So go back to the Liu and Lehoczky's bound where tasks are harmonically related, in the sense all periods are related in a way where if pi is greater than pj, then basically pi by pj is an integer, right? In the sense pj divides pi. So if you have a case where the periods are near harmonics of each other, then they should be scheduled on the same processor, because RMS guarantees the Liu and Lehoczky's bound. In this case, is very close to one. So if they are exact harmonics, it's one, right? Otherwise, it's quite close to one. Another approach could be that we could divide tasks into two groups based on whether they have low utilization or high utilization, where one third appears to be a good threshold, experimentally determined. So we take the small tasks and we schedule them separately. We take the large tasks and schedule them separately. Or what we could do is that we could create small large pairs, given that one has utilization less than a third and the other has utilization more than a third. You might try to group them and place them in the same CPU if possible. So the issues that we have to consider, again, kind of go back to the last lecture. Will we use a partition scheduling where we statically partition and then make local decisions? Or will we have one large single global queue where all the tasks are there? Furthermore, we need to look at our multiprocessing model. Are we looking at a distributed system, multi-core system, multiprocessor system, homogeneous, heterogeneous, etc.? And then, of course, the real-time parameters, which we have been discussing ad nauseum up till now, which means are they periodic or aperiodic tasks? Do they have dependencies, resource sharing, etc.? So what happens is that unfortunately, if you go back to the operating systems course, there was something called a Bellads anomaly, which said as we increase the number of page frames that are available, the page fault rate can actually increase instead of decreasing. Something quite similar happens. So basically, assume a set of tasks which is schedulable. If I increase the number of processors, or if I reduce their computation time, or if I weaken their precedence constraints, what can happen? In some cases, the worst case execution time, which I will also, by the way, refer to the response time because there is a confusion in the terminology. So when I refer to the execution time, it's the time that the task actually takes to execute, right? So this is, independent of the scheduling. But the point is that the response time is the time between the arrival of the task and the time in which the task actually completes its execution. So when I'm talking about the worst case execution time, it is nothing but the worst case response time, right? But for some reason, the community prefers worst case execution time when it actually means worst case response time. So the worst case response time actually increases when you expect it to decrease, in the sense when you provide more resources, you expect it to decrease, but in some cases it may increase, surprisingly so. That's an anomaly. So such schemes are known as runtime anomalies, where what can happen is that in a non-preemptive multiprocessor schedule where you will have resource constraints, a runtime anomaly may occur where the response time of a task will actually become quite high. It may exceed its deadline, in the sense it is possible that you had less resources, a task was meeting its deadline, you increase the resources, it started exceeding its deadline. So furthermore, there is a theorem that any work conserving scheme may lead to a runtime anomaly. So what is a work conserving scheme? A processor is said to be work conserving if, let's say, it is greedy, in the sense it is not idle when there is a task to execute. So which basically means a task comes, if it is idle, it picks it up for execution, it doesn't defer it, right? It doesn't choose idleness over execution, right? So well, why would you choose idleness? Because if you're expecting a high priority task to come after that, you may want to delay, because mind you, the multiprocessor system is non-preemptive, right? So both RMS and EDF were preemptive, but we are now looking at a non-preemptive system. So the issue over here is that such anomalies can make life tough. So let us look at four tasks. Task one starts with a phase of 0, in the sense arrives at the beginning. Executes for 20 time units, deadline is 22. Same T2 0 12 25, T3 10 8 26, T4 8 10 30. So you don't have to remember them, but we will, when we refer to this diagram, let's call this diagram A and this diagram B, we will be referring to these numbers. So now let us assume that there is a resource conflict between T3 and T4. So then let us first look at A, right? We have not come to this point yet. So what we will see is like this, that task T1 is schedulable. In a sense, the first 20 time units go for T1. Then given the fact that T2 comes in the beginning, we also do T2. Then T3 comes here at time unit 10, right? So which will just be before 12. So that's when T3 comes. We schedule T3, right? So T4 has also arrived at time unit 8. But let's say if we decide to schedule T3 first and then we have T4, nobody misses their deadline. So now what we do is we make a small change. So what we do is that we set the computation time of T1 to 10. All right. So if we change the computation time of T1 to 10, then T1 becomes shorter. But of course, when this finishes, so then T4 would have already arrived at 8. So T4 would be there. And T3 would also arrive at the same time. So here again, as you can see, something quite interesting can happen. If we decide to run T4 and not T3, because we can't run them together. So if we run T4 over here, So the total time is this is 10 units and the execution time of T4 is 8 units. So this is 0.18. After that, T3 will run. All right. So if T3 runs for 10 units, then it will finish at time 28, which is more than its deadline, which is 26. So as a result, T3 will miss its deadline. Given the fact that T3 will miss its deadline, what we see is that T3 was not missing its deadline in the sense it was completing early at 20. All right. In the previous regime, where T1 was much longer, in fact, twice as long. But if we reduce the execution time of T1 from 20 to 10, we expected the system to perform better. But in this case, it is not performing better, which is an example of the runtime anomaly that I was discussing. So let us now define predictability. So a scheduling algorithm is considered to be predictable if a decrease in the execution time or any other action in which I am nice to the system, which means I either reduce execution times or I increase the resources in the system, this will not lead to an increase in the total response time. Right? So, in a sense, the algorithm is well behaved without anomalies. So, there is a famous result by Ha and Liu in 1994 that all fixed priority algorithms, which are preemptive, so mind you, this is an important difference that I make. Instead of non preemptive, I say that these algorithms are preemptive. So in this case, all such algorithms are predictable, right? So our anomaly is arising in the previous slide because of the non-preemptivity. Also, there is something called the critical instant effect. So what happens is that under a fixed priority global scheduling regime, the worst case response time, I'm using this instead of WCET. So it does not necessarily occur when all the tasks are released at the same time. All right. Why is this the case? Well, the thing is, what we have seen in the earlier case, which was in the case of RMS, is that the worst case time happens when all the tasks are released at the same time. And if there is a small phase between them, it doesn't, it doesn't make the algorithm perform worse. It may not benefit you, but clearly it's not worse. But in the world of multiprocessors, that is not the case. So in this case, the worst case is definitely not when well, not definitely not, but you can't say with the same guarantee, in the sense the worst case is not uh, the instance is not the case where everything is released at the same time. It could be at, there could be other worst cases as well where the tasks have a phase. So this is the fundamental difference between uniprocessor scheduling and global scheduling. So what you can see is that in this case 1, 2, 3, and 4 are all executed at the, I'm sorry, all released at the same time. So you can see them completing at this point of time. But in this case, 1, 2, 3, and 4 are not released at the same time. So you see that 1 and 2 are released at the same time. So 1 and 2 execute. Mainly because these are the only two tasks you have. And also, it's a work conserving scheduler in the sense you don't want to leave any processor idle. So you leave it. But then if 3 and 4 appear later, could even be an epsilon time later, right? There is still a problem because 3 will execute here and 4 will execute here. You could have, reverted it, but that still, there would have been problems, right? No, I'm sorry, I stand corrected. 3 and 4 could arrive at times, right, at different times, in the sense 3 could arrive at this point of time and 4 could arrive, let's say, at this point of time. So at this point, 1 will finish, the processor will become idle, it will execute 3, it will not wait for 4. And when 4 comes, then it will not execute at the beginning, but when 2 finishes, it will execute. So the total execution time in this case will be much more than the total execution time when all the tasks came at the beginning. So in the case of multiprocessors, what happens is that knowing all the tasks really helps you, because the point is it helps you to schedule better, in the sense more is the information that you have, the more effective is the scheduling, which is something we didn't see in the case of uniprocessors. So in the case of uniprocessors, the worst case was clearly the time in which all the processors arrive, all the tasks arrived at the same time. So basically, optimal scheduling for uniprocessors has already been discussed. In the sense we have discussed static, dynamic, RMA, RMS, EDF. Complexities, well, it's linear for the rate monotonic scheduling because the tasks are static, right? So there is no difficulty in finding out the priority of a task. And in EDF, we have to maintain a priority queue, so hence it is log n. So in general, what we have seen that in the previous lecture as well. In multiprocessor and distributed systems, we need to partition the tasks between the cores. And this is an instance of the bin packing problem, which is NP hard. There's few important task assignment algorithms, right? In the case of a global scheduling regime, right? So even in a partition scheduling, a priori we will have to send tasks to different processors. So we will discuss the following algorithms: utilization balancing, next fit, and bin packing. And we will discuss two dynamic algorithms, which is focused addressing and bidding, and the buddy algorithm. So some implicit assumptions, right, which are assumptions we have been making up till now. Homogeneous processors, all processors are the same. Periodic tasks without dependencies, no resource constraints. Preemptible. Different overheads, this is something we will discuss. Global or partition, well, we will look at both. And how to assign priority, etc. This is again something we'll look at. So let's look at heuristic algorithms. So in this case, if we have multiple CPUs and all that we know is the utilization of a task, there are many things we could do. But fundamentally, what comes in our way is that if we are doing a static priority, we will run into the liu and Leyland bound, which is used to determine the schedulability on each processor. And of course, there are better bounds like the liu and Lewandowski's bound. So we will have those bounds. So then we will find the approximate number of processors to use. So the utilization balancing algorithm is very simple. We maintain all the tasks in a queue in an increasing order of their utilizations. So it's just a queue, increasing order of utilizations, right? So what we do is we remove tasks one by one in an increasing order. Then we allocate it to the lowest utilized CPU. Okay. So the thing is that we have multiple CPUs. So then what we do is that let's say we find the one with the least utilization because it's an increasing order, we allocate it here. The next one we allocate it here. So once we have done with one round of allocations, let's say we have this task, we find the one with the least utilization, which will be the first one because that's the way we chose it. Then we'll allocate it here. After that, of course, we will see which one is the lowest and then we allocate it there. So that's the idea. But the question is, will the mean utilization across all the CPUs, right, will that be equal to, the utilization of CPU I? Not necessarily. So this can lead to a degree of imbalance. Okay. So this can lead to a degree of imbalance, but the main idea or the philosophy behind this algorithm is to distribute the tasks with their utilization being the weight, such that all the CPUs roughly have the same utilization, but of course, they will never be exactly the same. So what is the objective again? It is to balance processor utilization, which is to allocate tasks one by one, right? Selecting the least utilized processor at that point. So then we come to the next fit algorithm for RMA. So the essence of the algorithm is like this, that if two tasks have a similar utilization, they're allocated to the same processor. So what we do is that we create n classes of tasks. So a task will belong to class J if and only if its utilization falls within this. So recall the Liu and Leyland bound, which was basically, the total needs to be less than this. So this looks like a similar formula, even though, this is more derived from a heuristic and experimental consideration. So in this case, if you look at, let's say, j being 1, so then this is 2 raised to power 1 minus 1, this is 1. And then this is 2 raised to power half, which is 1.414, right? Square root of 2. So this is 0.41. So what happens is that tasks with a high utilization, they get a large window, right? So the first j, for the first value of j, which is j equal to 1, that gets a large window. Then gradually, the size of these classes shrink. And for low utilizations, they're all put into the same bucket. So we basically create variable size buckets. Something, we have seen something quite similar, with our geometric approaches before, right? When we were dealing with a limited number of priority levels. So in this case, what we do is we create buckets of different sizes and we put in our tasks where clearly, the high priority tasks are in the ones with a large bucket, right? So what we do is that we define a utilization grid for the various classes. So as I said, class 1 is large, then 2 is smaller, 3 is even smaller, class 4 is even smaller, right? So basically, your large utilization tasks are sort of put into this large bucket. And the point is that we are kind of less selective over here for tasks with a high utilization. The main reason being that most likely they will exclusively get a CPU. So there is no reason for a more fine-grained differentiation. Whereas we do a much more fine-grained differentiation for low utilization tasks, right? Because, there we can do a lot of, we can push a lot of tasks into these small utilization holes that remain. So this strategy, well, it's the simulation studies show the results are not all that great. In the sense, the optimum number of processors that is required, right, which again can be found out using an exhaustive simulation by pretty much solving the NP hard problem. So the next fit algorithm requires 2.34 times the number. Okay. So the thing is that, one reason is that the sizes of classes are fairly coarse when you look at this, classes 1, 2, and 3. So that is why the bound is not all that great, right? In the sense that if the task set is schedulable with whatever n processors, then this may require something as high as 2.34 n, which is quite high. So then the thing is that if we look at bin packing for EDF, where the individual processors are scheduled using EDF, so in that context, let us discuss two bin packing algorithms, right? So as I said, primarily, the idea is that if I have a bunch of tasks where the utilization is known, so then I will have to, dispatch them to different per CPU queues, right, per processor queues, such that, of course, the net utilization in every processor remains below 1, right? But the question is, how do I minimize the number of processors? So that is exactly the bin packing problem. So one approach is phosphate random and the other is phosphate decreasing. So in phosphate random, the tasks are selected randomly and they are assigned to processors arbitrarily. So as long as the utilization of a processor does not exceed 1, you keep doing it. And experimentally, it was found out that if the optimal number of processors required is n, this requires 1.7 n, which is fine. So if you see our previous bound with, the kind of windows that we were making, right, with priorities, that was something as high as 2.34 n, but in this case it is much lower, 1.7 n. Then we have the first fit decreasing algorithm, which incidentally performs much better, right? Because here there is a logic, there is some heuristic. So the tasks are sorted in a decreasing order of their CPU utilization, right? We sort them like this. Then we select tasks one by one, right? So the tasks are selected one by one. So what we do is we assign it to the bin, in this case the processor, to which it can fit in, right? So the utilization will not exceed 1. So we essentially assign it to the processor in which it fits first. And we consider processors in decreasing order of utilization in the sense that in the previous case we look for empty processors, in this case we look for filled processors. In the sense that if this is the utilization level of different processors and a new task is coming in, so what we'll see is where does it fit first in decreasing orders. We'll consider this processor first. If it fits here, we'll fit the job. If it doesn't fit here, we'll go here, and finally to an empty processor, right? In an empty processor, basically empty bin. In this case, no task has been scheduled. So if we go this way, where we try to, try to fill everything and, try to keep filling, and also our order of priority is where, we have these filled bins. And the order of priorities that we look at the cumulative utilization of a bin or a processor, and we proceed in a decreasing order of utilization. So here the optimality results are much, much better. So we are 1.22 times the optimal number. Okay, so we are not very far. So we have seen three numbers, okay, albeit in different settings and different algorithms. But 2.34 and 1.77 were not acceptable. 1.22 seems okay. So now let's come to dynamic allocation of tasks. So this is primarily required when tasks arrive asynchronously at different nodes. They are known, it's not known in advance which tasks will arrive, and they have to be assigned to processors as and when they arise. Needless to say, there is a high runtime overhead. The allocator at every node needs to keep track of the load positions of other nodes such that tasks can possibly migrate. So we have two algorithms here, focused addressing and bidding, which has high overheads, and the buddy algorithm, which has low overheads. So in this case, every processor maintains two tables, the status table and the system load table. So the status table is like this, that it maintains the execution time and the period slash deadlines of the tasks which it has committed to run, which means that these are the ones that are going to run on the processor. So mind you, these are processor wise or CPU wise tables, and the system load table has the latest load information of all other processors in the system. So if you consider the rest of the system, so it is basically what one CPU thinks about the rest, right? So may not be up to date information, but still it maintains this table. Now the question with focused addressing and bidding is like this, that the time axis is something that we divide into intervals or windows, where a window is an interval of a fixed duration. At the end of each window, each processor broadcasts the fraction of its computing power in the next window that is currently free. So because we have a set of committed tasks, we have a set of periodic tasks, a set of tasks which have come. So already certain commitments have to be made. So let's say that is taking up 70% of the window. Then a processor lets the other process know that look, 30% of the window is still free. So every processor on receiving a broadcast will update the system load table. So now the issue is that when new tasks arrive at a node or arise at a node, both being the same, the node first checks if the task can be processed locally. If yes, then no problem, it just updates its status table. So mind you, it of course its load will change. In an ideal setting, it should be broadcasting this information to others, but that may create too much of messages. But it also introduces the possibility where there will be a mismatch in the information that is stored, but we need to take that into account. The interesting case comes when we don't have enough bandwidth, enough time in the next window to execute this task. So then the processor will examine the system load table to look or search for a processor to which this task can be offloaded. So what it does is it creates a request for bid and RFB. So the overloaded node will send out RFB's request for bids, right, to basically the lightly loaded processors. So these are known as the focused processors. That is why we call it focused address bidding. So the key point is that the information in the system load table may be out of date. So because it is out of date, not all such offloading attempts will be successful. But nonetheless, this is our chances are high if we focus on the processors whose current load is low. So by the time the processor gets the RFP, the focus processor might have become overloaded. So then, of course, there is a problem. It will then have to say that, look, I can't do this job, right? So the point is that, these algorithms have a high communication overhead because we need to periodically transmit the status messages to update the system load table. And also because of this focused addressing and bidding, and as I said, not all bid requests should will be accepted. The reason being that the status of the node may have changed. So in that case, the requester will have to consider sending requests to other possible processors, right, in its list. So clearly a lot depends on the window size. So the window size is large, it will reduce the communication overhead, but it will also increase the level of mismatch between the information that is there, in the status table of one processor and the system load table of another processor, which, tracks what is the utilization, right? So basically, you will have more obsolete information in the system. So this is why we have the BodySet algorithm, which tries to overcome this. Overcome what? The high communication overhead. So here the idea is that you don't target all the processors, you target a few, right? So you reduce your domain of interest. So a processor can be in one of the following two states. So this is more like a binary protocol, right? It can either be underloaded, where the utilization is less than a threshold, or it can be overloaded, right, where the utilization is more than a threshold. Only these two things. Periodic broadcasts are not required. Only when the status changes from underloaded to overloaded do you send a message, or vice versa. So this reduces the number of messages in the system substantially. Furthermore, whenever the status of a processor changes, it does not broadcast this information to all processors. Instead, it broadcasts it to a subset of processors, which it calls its buddy set. So the buddy set are the processors which are kind of close by, nearby, right? You could also add other application specific logic. But in general, this is not a piece of information that is sent to everybody. So this further reduces the bandwidth. So the design of the buddy set is an important parameter, is a very crucial parameter. Should not be too large, should not be too small. Furthermore, in multi-hop networks, the buddy set of a processor typically is comprised of its nearest neighbors, right? So in a sense, you just offload to your neighbors, not to faraway nodes. So this is quite practical. And so the point is that you basically choose one of your lightly loaded neighbors. So go back to this description over here, overloaded and underloaded. So just find an underloaded neighbor in your buddy set and then try to request it to accept your job. So the node state, as we have seen, is threshold based, right? And any time that a task at the local node fails an admission test, in the sense we see that all the tasks will not be schedulable anymore, that is when you consider the possibility of a transfer, migration. So there are two policies. One is the information policy, which is that how exactly and how frequently do you inform your buddy set and how large is the buddy set. So of course, you can be very eager in the sense whenever there is a change, it is sent to the buddy set. The other is the transfer policy. So that is that, which buddy do you choose and, how do you make the load information based on the load information available, who do you choose as the receiver and then, you request it, the requester will say either yes or no. And based on that, you transfer the job, right? So there are two important policies or two decision making points here. How do you share information and how do you do the ultimate job transfer? So there are other aspects to scheduling, right, beyond performance as we have seen. So we have just seen, two dynamic algorithms, right, focused address bidding and the buddy algorithm. And we have looked at different ways of distributing tasks, pretty much, heuristics for bin packing. But we can also do things like fault tolerance in the sense that if, let's say, one process may develop a fault, we can run multiple copies of the process on different CPUs. So, of course, this will harm our real time guarantees, but we will get a degree of fault tolerance. So, we'll basically schedule secondary copies or ghost copies, which will be redundant copies of a primary task. Furthermore, we may schedule or create ghost copies which are not exactly identical to the primary copy. They may be in a certain sense reduced. So why would you want to do that? Well, the main idea would be that, look, in case there is a failure, we would want some sort of a graceful degradation. So for example, let's say that, we are finding features in an image. So to reduce the load on the system, the secondary copy may actually not look at the full image, may be looking at a reduced part of the image or an image with a reduced granularity. This will make it run faster and reduce the load on the system and also provide a degree of fault tolerance. If the primary successfully executes, no problem, just cancel the ghost. As you can see over here, that the P's are the primary tasks and B's are the backup tasks. And in fact, you can schedule two backup tasks at the same time. So of course, you can't run two tasks on the processor on a processor at the same time. At runtime, you will have to choose which one you need to run based on, application specific priorities. So this finishes our discussion, broadly speaking, on scheduling, both uniprocessor scheduling as well as multiprocessor scheduling. So that completes over here. From the subsequent lectures, we will discuss more about practical real world real time operating systems.